So while we're setting up, I'll introduce our next speaker, which is Ryan Baumbach. Ryan is at the National High Magnetic Field Lab in Tallahassee. I don't know what your title is these days. It's not.
That's beside the point.
Physicist.
Yeah, physicist.
I actually spent some time with Ryan when I was postdoc at UC San Diego. That's why I think it's real. So he's done lots of crystal synthesis over the years. That USB?
Whatever the heck this is. Yeah, try this.
Right.
Yes, it fits.
No.
I'm here. All right, excellent. Okay.
There's a point here. Okay. Audio?
Audio?
Right.
Okay. All right, we're in business. So, well, first of all, I want to thank the organizers and my old friends, JP and Nick, for the invitation to be here. It's really a pleasure. I love this school, and I think it's a great service to the community. So thanks for doing this year after year. Awesome. My name is Ryan Baumbach. I'm a scientist. My home base is at the National High Magnetic Field Laboratory in Tallahassee, Florida. I just want to take a brief moment here. I don't know if people are familiar with the Mag Lab, but it's a user facility that you all can come to. You know, you just write a experiment proposal and it's all free of charge except getting you there. We have a site in Tallahassee that focuses on high, long-lived or DC magnetic fields. There's all sorts of research faculty there that can make the experiment happen for you. So that's awesome. And then there's also a pulsed field facility in Los Alamos and what's called a high B over T facility in Gainesville. And what that really is a facility where they use adiabatic demagnetization refrigerators to get to really low temperatures. So if you're interested in the Mag Lab, this is my little pitch for it. Just talk to me after this and I'll give you whatever sort of information you want to have. So in my group, what we're interested in primarily are quantum materials. And we're especially interested in designing and synthesizing, or maybe prospecting and synthesizing new materials. So this is new materials business. And that's what we're focused on. And in particular, I care a lot about strongly correlated F-electron systems. But a lot of what I'm going to talk about here can just be applied broadly to all sorts of different classes of materials. And so when we're trying to deal with these sorts of things, what we're thinking about are some sort of generic questions that are always swirling in our minds. And this includes things like, how do you even choose what to grow, right? The periodic table is just enormous. And not only that, but when you make, you know, binary and ternary combinations, quaternary and whatever, the number of combinations is way beyond what we could possibly achieve, even if all of us dropped everything right now and spent the rest of our lives just growing new combinations. So we have to make choices. We actually don't really know how to make choices, but I'll give you a little bit of perspective on that. Okay, if we're going to make choices, we also have to have some understanding, and not just of electronic and magnetic phase diagrams, but also chemical phase diagrams. So JP asked me to talk about binary phase diagrams. Everything I know about them comes from, I don't know, sort of teaching myself. I never took an actual course in it because I'm a physicist. But what happens when you're in this line of work is that you start to impersonate an inorganic chemist, or you start to impersonate a material scientist. So I'll do my best. Yeah, we're all in the same boat. So I'll do my best to tell you about binary phase diagrams, but I think there's other people who can give you a much more thorough, perspective on that. So don't ask me hard questions, ask me easy questions. And then finally, in this talk, we're going to think about the chemical phase space, and then I want to talk about how different elements have different personalities. And what that leads us to is a necessity of using all sorts of different synthesis methods. So we saw this fantastic video of sulfur exploding, right? Actually, I want a copy of that if I can have it. This makes the point perfectly. Different elements have different personalities, and it forces us to really think carefully about how we're going to deal with them so that we don't kill ourselves, but also so that we can grow beautiful crystals. And so that's what we're going to do. And to start with, I'm just going to start really broad and say that one of the things, and I think I'm probably preaching to the choir, but one of the things that's really separates modern society from even 100 years ago is that we now have literally thousands of different materials that are optimized to specific tasks. And this isn't just, our solid state crystalline materials. There's biomedical materials, there's engineering materials, there's structural materials, whatever. But the class that I think we're all interested in are these so-called quantum materials. And we can get into arguments about how the term quantum material doesn't actually mean anything. It's too broad. But I just want to make a definition. When I think of a quantum material, I think these are types of materials where the wave-like character of the electrons take over. We also have quantum spins. We have structural degrees of freedom and orbital degrees of freedom. And all of these things are mixing together in unique ways. We're pulling different parts of the periodic table to get these different flavors, or if you want different parts of the Hamiltonian to create the behaviors that we want, right? And this is also where I like to sort of stick a little screw in other fields of physics. High energy physicists, nuclear physicists, astrophysicists, they get to study one universe. As condensed matter physicists, from a basic science and applied viewpoint, we're really lucky because each one of these different crystalline structures is a universe unto itself, right? So we get to study so many different universes from the perspective of electrons. And sure, some of them are sort of, universality classes, right? A Fermi liquid's a Fermi liquid, or a BCS superconductor is a BCS superconductor. But when we think about new materials physics, we can also contemplate the idea that there's new physics out there that's just waiting for us to come and find it. And that's part of why it's exciting. The other reason it's exciting, I think, is because these quantum materials are actually useful for society. You have a prospect of discovering something, and within your lifetime, seeing it brought to an actual application. That's really incredible. And just to make an arbitrary distinction, we can think about classical quantum materials. And to me, these are materials where the basic science is pretty well understood, and we've seen them brought to actual applications. So for example, conventional superconductors are used in things like medical MRIs, particle accelerators, fusion, or semiconductors and permanent magnets. And while we may understand the science of these things really well, there's still tremendous effort going on to improve them and bring them into actual application. So that's an important area. And then the other one are sort of our next generation quantum materials, where there's so many open possibilities. We may not understand the basic science, and we may not even yet have the ability to envision what they're actually going to be useful for, right? But just some examples include things like qubits, quantum teleportation, quantum sensors, like we just heard about, the two-dimensional systems, the quantum flatland, some people call it. And then my own favorite area are materials with strong electronic correlations, protected topologies, magnetic frustration, so on and so forth. All right, so we have this huge array of chemical combinations, and we have a huge array of physical properties that we can start to think about. And so, I don't know, I find myself in the lab sort of overwhelmed with this perspective all the time. And we have to think about how are we actually going to choose what we're going to do. And I want to give you two perspectives on this. And I think that probably you could tell me even more. I'll give you two simple perspectives. And I think the first one is that you ought to think about the degrees of freedom that might be present in something and then think about what you might expect to find in that type of material. So an example of this, just my own personal favorite class of materials are F electron materials. And what do we know about them, without thinking at all? It's that the F shell is tightly localized around the nucleus, right? And the effect of this is that it produces local moment magnetism with a lot of anisotropy. That's sort of our most basic assumption. So the F shell produces magnetism, right? And this is a path that people followed, starting sometime in the middle of the 20th century up to present. And it's, I can't possibly summarize all the thousands of magnets that are based on lanthanides, but there's so many. And I just point out, a few well-known examples here, including neodymium iron boride. So this kind of works. You have an idea of what you might see, and you go and find it. But it turns out that as you do this, there's lots of surprises, right? And what happened as people studied F electron intermetallics is they realized that lots of other degrees of freedom are available in these systems. And just to give a quick summary of this, this includes things like electronic hybridization for some of these elements. So elements like cerium or ytterbium or uranium, plutonium, and a few others, you can have mixing between the F and the conduction electron states, which leads to behaviors like condo lattices, heavy fermion ground states, so on and so forth. This, I think, was totally unexpected, but it has had a profound effect on how this field has advanced. Within these materials, there are also unconventional superconductors where the pairing mechanism is not just, phonon mediated, but it might be electronic or magnetically mediated, or something else, even more complicated than that. So that's a great benefit. And then there's even other exotic electronic and magnetic states that we just don't understand very well at this point, right? And so the point that I want to make here is not really that I want to tell you about any one of these specific states, but that by having a reasonable hypothesis, F electrons will give us magnetism. If we go out into the chemical phase space and we just start turning over the soil, you're going to let the conditions emerge for serendipity to appear. That's a major vector for pushing forward fields like this, right? New materials physics depends on this in a real way. In addition to this, there's a separate vector, which actually, the previous speaker did way more beautifully than I can. And that is just to say that sample quality matters, right? And the example we saw is trying to go into the quantum limit. You can only really get there by making better and better samples. And people have invested a tremendous amount of time in this. Amongst F electron materials, there's another example that's very recent, which I'm actually kind of embarrassed to even present here because the real experts are right here, JP and Nick and others. But there's this example of uranium tellurium 2, which if you don't know, was recently shown to be a really unusual superconductor called the Lazarus superconductor. I think Nick's responsible for that. Anyways, the mag lab is responsible. Okay, it all comes back to the mag lab. So this is an amazing material. But the story that I want to tell you here has to do with sample quality, right? And so to my knowledge, one of the first times this was studied was back in the early 2000s by a group in Japan. That's shown in this sort of, upper gray curve here. These samples were produced using a molten metal flux growth, which I'll talk more about later. And the outcome was that it actually happened to produce samples that weren't especially high quality. They also didn't show superconductivity. So there was no activity on this material besides this, early publication until 2019, when Sheng Ran and JP and Nick carried out an iodine vapor transport method, which is completely different from the self-flux methods. And the resulting crystals were more like this. They're higher quality, and sure enough, superconductivity shows up. Okay? So that's a huge step forward in this material. Since then, there have been all sorts of attempts to improve the sample quality that results in an increasing TC, decreasing residual resistivity. And then very recently, there's this new molten salt flux technique, which again is different. And it seems to produce especially high quality samples, right? So long story short,
I want to comment on serendipity.
What's that?
We weren't even trying to think.
That's what I thought. I wasn't sure about that. So let me just tell you this. These are two axes, right? Like serendipity and improving sample quality that are intersecting with each other. And they're both always at play when you're working on new materials physics. Were you trying to grow uranium, tellurium, antimony?
That was the seventh.
Okay, so,
Yeah.
oh, it's the 712. Okay, so, okay, these are two important axes that we have to keep in mind. Okay, and you can imagine this is challenging.
Good question.
What's that? Where's the question?
Do people understand what are the disorder or defects that is account for the losing of superconductivity or?
I don't think there's a quantitative understanding of the defects yet. Yeah, yeah, okay. So this problem of creating new materials is challenging. And if we want to try to address it, we have to have at least a few things, in our list of tools. So we have to have or develop a familiarity with the fundamental degrees of freedom, right? Like F electrons make magnetism, but what else? At the same time, we have to be thinking about the relationships between chemical and structural degrees of freedom and how they relate to electronic and magnetic trends in real materials. Then we're going to go out, we're going to start sifting through the chemical structural phase space. And really the point of this is to make room for serendipity. We think we know what we're doing, but nature actually has other plans. And then as we do this, we have to have a commitment to refining quality. And all of that can add up to progress. But the reality is that as we do this, physics, chemistry, and material science have to work in harmony. And anyone that wants to do this business may start off as a physicist, but in the end, they're going to become a fake chemist and a fake material scientist and, right? You have to be sort of a jack of all trades in order to be able to do this sort of work. Okay, now before I go on, I'm going to switch gears now and stop talking about my perspective on it and give some, more concrete information about how you do these things. But I just want to bring your attention to some references that will probably be helpful. This book by Pamplin is in some way the granddaddy of how you want to think about learning about crystal growth. This book from this FQM conference, I think is awesome. It's more modern and probably JP gets some proceeds from it. And then finally,
let me just say too that we have a copy of that book for you guys.
yeah, it's a fantastic book. You should read it and really take it seriously. And then finally, we saw that sulfur explosion. This connects to something that I really want to say, and that is that when we go out into the periodic table, there's a lot of danger involved, and you need to be really thoughtful about your own health and safety. And so, of course, we can go and read MSDS data sheets and material safety data sheets, but I don't know how many people have ever read one of those. Yeah, I've tried. First of all, they're next to impossible to read. And second of all, no matter what you read, it's going to sound like it's going to kill you, right? Like it's all going to kill you and it's going to be unpleasant. So those aren't that helpful. What you really want to do is pick up a book like this. And this one, I think, is especially good. The other way that you can figure out how to be safe is to talk to people. So even if you have a competitor that's working on a particular material, I think that a part of what they'll be willing to do is to talk to you about the safety considerations surrounding a material. Right, so talk to people, talk to me, JP, Nick, whoever, our speakers, Jim. People want to talk about this because generally speaking, we don't want to have these accidents, happening in labs, because that is detrimental to the field. Okay, so we want to think about that. But now let's go ahead and look towards the periodic table and think about what we can actually do. And I think you want to think of the periodic table as being sort of a quantum materials foundry. And the first thing that you think about here are sort of the degrees of freedom that you can get, right? Not all parts of the periodic table are the same. And we need to use these different parts sort of selectively. So how do we think about that? Well, we can think about different parts where, for example, if you go to the alkali metals and alkaline earths, you can start to think about tuning the unit cell size and band filling. If we go to very light elements, we can think about strong bonding and high phonon frequencies. That's the premise behind the hydrogen superconductors, things like magnesium diboride. If we go into the P block, we can think about tuning the unit cell size, the bandwidth, and band filling. Amongst transition metals, up at the 3Ds, we can tune the density of states and have some expectation of magnetism. I say fragile, but it's not always so fragile. And you can go deep into the transition metals and you can pick up strong spin orbit coupling. And then finally, what about the F block? Well, you can get local moment magnetism. There's something called the lanthanide contraction, where the size of these decreases as you go across the series. For some of them, like cerium and ytterbium, and europium and samarium, there's valence instabilities, hybridization, crystal electric field effects, spin orbit, so on and so forth. And all of this sort of gets compounded as you go down into the 5S. Right, so at least as a naive chef, these are the ingredients that you might think about using. Okay, but as we do this, we don't just think about the electronic and magnetic degrees. We also have to remember that different elements have different personalities. And as a result, the growth methods have to be tailored to the desired product. All right, so let's go through these one more time and think about what those personalities are like. Oh, I already had one. Okay, so to start with, if we think about the alkali metals and alkaline earths, what we see is that they tend to be air sensitive and easy to melt. Okay, that sort of sets one class of growth parameters you might think about. As you make your way into the transition metals, they tend to be not air sensitive and significantly harder to melt in some cases. We go into things like light elements, boron and carbon. Well, they're super abundant, so wouldn't it be great if we could make everything out of them? But there's a lot of technical issues with them. They're hard to melt and dissolve into things. P block, they tend to be poisonous and have high vapor pressures. A little bit more, to the left in the P block, they are easy to melt. They're easy to react with things, but some of them are pretty poisonous, like thallium's a problem. You don't really want to go there. And then for F elements, they can be air sensitive, but somewhat hard to melt. And then if we get into the 5F series, and I honestly do think that if there weren't so many problems with these elements, we'd all be studying them all the time because they're so dang interesting. But there's big problems. They tend to be air sensitive. Many of them are really poisonous. They can be very radioactive. And what's more, once you make it past plutonium, they're synthetic, right? So most people can't even get their hands on them. Okay, but they're a great ingredient for uncovering interesting new behaviors, right? So, and these are the properties of the individual elements. We also just need to think about how they interact with each other. So now we're going to go ahead and start to think about binary phase diagrams. And I think that in a way, I'm going to give you a really rudimentary introduction to binary phase diagrams with no math and just try to focus on what can you actually use these things for. Right, so here's an example of a binary phase diagram. This is a binary chemical phase diagram. And we're all used to thinking about electronic and magnetic phase diagrams, but we also have to think from this chemical perspective. Right? And what's shown here, and by the way, I stole this from this excellent paper by Paul Canfield. I highly recommend that in addition to those references I showed earlier, that you read this carefully, because actually you'll learn more from this than from my talk. So read this paper. In any case, here's a generic phase diagram where we have element A and element B. Okay? And the first thing that you want to notice about this is that there's a bunch of lines, that are moving sort of through peaks and valleys. And then there's some vertical lines and some horizontal lines. So what does all of this mean? Well, the first thing is that up here in the high temperature region, and I should have said this, temperature is on the y-axis, and on the x-axis is the chemical composition. And this is a little confusing. I get confused by this all the time. This means it's 100% A, right? And this means it's 100% B. So 0 doesn't mean 0A, it means 0B. Okay, my students and I get confused by that all the time. Okay, so we've got this separation between the liquid and the solid phases, and then we can start to think about what these different lines mean in the phase diagram. And the first thing that I think is probably self-evident, I'll just say it, is that these lines that come down are labeled by A2B or AB, or in other ones, I'll show you in a minute, there can be a lot more things going on. These represent the chemical phases, the crystalline stoichiometric chemical phases that can be formed by combinations of these elements, right? So these are the compounds that will form out of these mixtures. And then everywhere else, it's, sort of an alloy random mixture of at that concentration. Okay, now there's some features that you want to think about here. And the first one is something called a congruently melting compound, or sometimes people call this a line compound. And what this is a compound that extends all the way up to the melt, and you have an interface between the solid phase and the melt phase. Right, so in order to access something like this, the most obvious thing to do is just combine these elements in this ratio, heat it up as high as you can, get it in the liquid state, and then drop the temperature back down. And that's straightforward. In a way, this is the absolute easiest type of material to grow, except that in practice, you're probably going to run into some limitations. And I'll return to this a little bit more later, but let me just say, what if this melting temperature is way above a temperature you can reach in your furnace? That's a problem. What if one of these elements has a high vapor pressure? That's a problem. So just because it's the simplest sort of feature in the phase diagram doesn't necessarily mean it's the simplest thing to actually grow. Okay, so we can go on to another one. Oops. Right? So now what about these guys that don't make it all the way up to the melt? Right, so this A2B phase present here, and it gets cut off by this line. What this is something called an incongruently melting or paratectic phase. Okay, and so there's a few ways to think about this. One is that if I combine these elements A and B, and I heat them up into the melt, and then I drop down here, what's going to happen is that I'm going to get a mess, right? Because when I enter this phase here, I'm going to get a combination of some crystalline phases that will drop out depending on how fast I come through here. You get some A2B and some AB, as well as just a sort of, mixed up alloy of A and B. Okay? A different way of putting this, let's come from the lower temperature part. If I take A and B, in their solid forms, kind of grind them up, mix them together, I can heat up at this temperature, and as long as I don't cross this decomposition line, sit around somewhere like here, and eventually they'll react through solid state reaction or diffusion or whatever to form this A2B phase. But that will only ever form a polycrystalline material, and it may take a very long time. Right? But this was the route by which cuprates, for example, were originally developed, and it's useful in a lot of ways. Okay, so these are two distinct paths to producing compounds: congruently melting and incongruently melting. Okay, and there's one other sort of feature that's useful for crystal growth that you want to think about in these phase diagrams, and that's these minima. Like I said, I'm not going to do any math. I won't talk about the lever rule. But I want to point these out because they're really useful. There are places in phase diagrams where you actually get minima in your melting temperatures. Right? These are referred to as eutectic points, and as you'll see later on, this is especially useful when we're thinking about molten metal flux growth techniques, right? We're always looking for ways to manage vapor pressure, to dissolve elements into each other, and to get into temperature ranges that we can actually reach in cheap furnaces, right? Not everyone can afford the expensive furnaces, and even if you can, they're going to break all the time. So if you can bring it to lower temperatures, that's a good thing. All right, so here's an example of a real binary phase diagram. This is just cerium and tin. And actually, there's one thing that I wanted to mention earlier, and that is just that during the 20th century, there was a huge effort in the US, and in Russia, and in Europe, and probably elsewhere too, just to experimentally map out the phases that form in binary mixtures of elements throughout the periodic table, right? There's also theoretical predictions for what phase diagrams should look like. The point is that you can access these things either through the ASM database, or maybe your department has these huge tomes that you can actually page through and learn about what these combinations look like. And I have to say that as a graduate student, for a long time, I was totally unaware of this. And if you haven't encountered this before, that's okay. But it's a good idea to start paging through these things as you think about the types of growths that you might want to do, because they give you real insights. For example, here,
How reliable do you believe these?
I was going to say that. Let me, that's like my next statement. Yeah. Okay, so what I want to say is you can see all these phases that form, and so on and so forth. You can get an idea of what these melting lines might look like. But something that I think is actually really attractive, I see it as not a disadvantage, but rather an advantage. It's that all of these things are a little bit approximate, right? The actual melting lines may not be actually very well established. And what's more, there may be phases that are present, deep within the phase diagrams that just haven't been discovered yet. Right? This is a point that Paul Canfield makes all the time, and I think it's really true. Don't take these things as proven. They're more like it's like explorers in the old days with kind of a bad map. You get an idea of where things are, but it's not necessarily like that.
So these phase diagrams are all, or so far just temperature phase diagrams, but obviously there are other things like pressure, field.
That's true. That's true. Yeah.
And so are these temperature diagrams all at like zero field and
Yes.
some like at 1
Atmosphere. Yeah. Unless it says otherwise, you can assume that it's 0 field and 1 atmosphere. It's funny that you bring that up because if I have time at the end of this, maybe I took it out. But one of the things we're working on at the Mag Lab is starting to explore the influence of magnetic field on crystal growth. And I actually think that's a sort of a wide open area. The influence of applied pressure on crystal growth is better explored, and it has, some clear advantages. Okay.
Just one more thing, just to address your question. Very often, I mean, not all the time, but the melting points are data, right? So you see the numbers there. Not the data, but the rest is kind of.
It's just extrapolated.
Or the theory, or a combination.
Yeah. So there's truly a lot of room in binary phase diagrams for discoveries, and we overlook that all the time. But there's a lot of work to do there still. Okay, now let's move on and think a little bit more about how we might use the phase diagram to get things that we want. Okay, so we have these phases A, 2B, and AB. Let's first focus on the incongruently melting ones, which we can't just melt it and get it. And sure, we could do a solid state reaction and get a polycrystal, but is there some other way to get this sort of material? And the answer is yes. What we can do is do a growth of A2B out of an excess of the A element. So that's this arrow here. And what we do, we'll make this combination, we'll heat it up into the liquid state, and then we'll slowly start to decrease the temperature. And what will happen is as we encounter this solidification boundary, we'll start to drop out the A2B phase, okay? And as we do that, what's going to happen is that the B element's going to get depleted and the melting temperature will drop a little bit. And then we can drop out some more A2B, temperature will drop a little more, so on and so forth, all the way down to the eutectic. And what's powerful about this is not just that you can make this phase, but depending on how we decrease temperature, I mean, we can do it fast and we can nucleate everything all at once. That wouldn't be so helpful. But if we do it slowly, we can nucleate very slowly, and in that way, actually produce beautiful single crystals. And this is the fundamental idea behind the molten metal flux growth technique. And I'll expand on it a little bit more later, but just keep this in mind. So this is what's behind all solution growths. And then there's math, and I'm not going to talk about that. Okay, what about AB? Okay, so AB, sure, we can heat it up, liquefy it, and cool down. But there's problems, the ones I already mentioned, and then there's one more. And that is this question of how you nucleate the crystals, right? If you go up here and you pass through the solidification boundary quickly, you're going to wind up with lots and lots of nucleation sites, and you'll wind up with basically a polycrystal. That may not really be what you want. I'm going to tell a little bit more about how to get around that from a direct melt later on. But for now, let's just again think about these solution growths, and we can basically pull the same trick. We can go ahead and think about growing AB out of an excess of A. But here you'll notice that there's a little bit of a disadvantage, and that is that we're not just going to grow AB. We're also going to produce this A2B potentially, right? So that's That's a challenge, but we can get around that in this phase diagram by going just to the other side. We can do a growth of AB out of an excess of B, and now we're happy. All right, but in reality, things are never quite so simple, because what if, B is a problematic element? What if it's expensive? What if it has vapor pressure properties we don't like, so on and so forth? That's one thing. And then the other thing that can get in our way is just that the way that nucleation works in different melts can vary depending on what part of the phase diagram you're in. Right, so the reality is that if you wanted to make this AB phase in the lab, you're probably going to try a few different things. You're going to probably go here, probably go here. You might even, go ahead and try to do that direct melt. So that's the, the sort of the art of producing what you want. There's a lot of work involved, but at least you have an idea now of how you would actually go about getting that. Oh man, I'm down to 5 minutes already.
Well, 7.
7 minutes, okay. Yes.
How broad are these lines in
Yeah,
practice?
okay, so some of them have a width and some of them don't. Okay, and when they have a width, it means that there's a compositional span where the crystal structure will form, but you may have variation in the filling of the site. And that varies material by material. Okay, let me try to go a little faster and try and cover a little bit more. I do this every time. But I just want to say that, we don't all want to grow binaries. We also want to think about ternaries. There are such things as ternary phase diagrams, but they're not well developed, right? And they usually don't give you the map as a function of composition and of temperature. Although there are active, works going on to develop that for specific combinations of elements. But if you want to start to get an idea of how this works, what you can do is take any collection of binary phase diagrams, array them in this way, and then start to imagine what the solidification boundaries might look like based on these cuts. This is not a trivial thing to do, but I think it's sort of what we have to work with when you think about doing this. And I just wanted to show you this because it's fun. Thinking about eutectics, we can take advantage of that in ternary systems too. This is a piece of Gallon sand, which is just a mixture of gallium, indium, and tin, which are all solids at room temperature. But if you mix them together in the right ratio, that melting temperature actually goes below room temperature. So this is fun if you want to, do outreach at schools and things like that. But we can also think about, using binaries and ternaries and so on in order to access eutectics that can be useful in our crystal growth activities. All right, so that's our binary phase diagrams. Now we want to apply them, in various different settings. And to summarize, more or less all crystal growth techniques are going to fall into one of these categories. So solution growths, which we've heard about, vapor phase growths, which we've heard about, thin film growths, 2D layering and stacking, which is a relatively recent development, but is really powerful, and then direct melt growths, right? And so what I'm going to do with the time I've got left is really just focus on these two. I want to tell about direct melts and some of the ways you can do this, and then the flux growth methods. All right, so let's think about direct melts. Well, the first thing that I want you to know is that they're really only applicable for congruently melting systems. If it's incongruently melting, you're going to wind up with a mess. And that's terrible. Right, so really steer your attention towards direct or to congruently melting phases if you want to do these direct melts. What this all boils down to is how you're going to heat the material and how you're going to control the way that the crystal nucleates, right? That's the bottom line with all the different approaches to direct melts, right? I said this already. And one of the most powerful ways or common ways that we'll actually access direct melts is through something called an arc furnace. I guess you're all going to get some experience with this later on today, so I won't show my video, even though it's a really cool video. But I just want to say that the idea here is that in an arc furnace, you'll have a container that you can evacuate and then refill with the inert gas. Going into this will be an electrode that's attached to a welding power supply. There'll also be something like a copper hearth provide the path for the electrical current. Turn on the power supply, discharge the electrical current through this, and heat things up to really high temperatures over a really short time period.
You can show the video.
I'll show the video. It's a cool video. All right, so this is our arc furnace in action. What we're going to do is strike the arc. Here we go. Okay, it's super bright. You have to wear protective eyewear. It's going to go onto this piece of zirconium metal, and you'll see that very rapidly, even though this is a high melting temperature material, we're converting this into a liquid phase. I just like this video because you can see it flow down into a pot. This is pretty normal and what you would expect to see in this sort of thing. You can imagine, this is simple. I'm just melting a piece of zirconium, but if I had a bunch of other elements in there, I would be combining them very effectively. All right, so we're going to let this go. There's one more thing that I want to show you here. And that is that when we cut off the plume, that flash was the shade on the, the dark shade changing. But the main point that I want to make here is you see how quickly this is cooling down. When you're in an arc furnace, you're potentially as high as 3,500 degrees C. And now this is cooled down below 600 degrees C in a matter of like 10 or 20 seconds. Right, so you have absolutely no control over the heating and cooling profile. That's a limitation on this sort of growth. All right, so arc furnace, what do we get? We get high temperatures. We get rapid throughput reactions because this is so easy, right? It lets us look at a lot of the chemical phase space. But some other things, okay, tends to produce polycrystalline material because it's such a fast process. The nucleation happens everywhere all at once, and you have no control over that. But I will say that sometimes crystals will form large enough grains that you can actually cleave off pieces. And if you want to make a measurement on a very small sample, you effectively have a single crystal. Okay. What else is this useful for? Well, one is preparation of raw elements. In Tallahassee, it's incredibly humid. If I store my powder metal out in the room, I think this is zirconium, kind of looks okay. But I'm going to go ahead and arc melt it just to put it into a little piece and I get a nice shiny boule. Look at all this other junk around it, right? That would have gone into my growth otherwise. So arc melting is a poor man's way of cleaning materials. In addition to that, we use it for preparation of refractory crucibles. So this is a tantalum tube, which generally speaking is difficult to work with to make a sealed vessel. But with an arc furnace, we can do that. We can carry out reactions inside of here. So, we heard about alumina crucibles, but in fact, there's many other types of crucibles that we need to think about if we're dealing with elements that are very reactive. So tantalum is one powerful way to do this. There's other important considerations, like the fact that you actually need to be able to melt the material. In other words, it needs to be kind of metallic so that electrons can move through it. We need to avoid high vapor pressure elements. I once arc melted phosphorus, and was that a mess? Yes. And some other elements are just kind of weird actors, like manganese. You can arc melt it once, it seems to clean it out, and then when you arc melt it again, it kind of likes to fracture. So these are all things you have to think about. I know that I'm really low on time, but I'll just hit this up too.
You can 5 more minutes.
Okay, 5 more minutes. Okay, excellent. Okay, so arc furnace is our most rudimentary but really powerful way to access direct melts. But we can be a lot more controlled than that. There's a million different ways to heat samples. And one that I like especially is using something called an induction furnace. That's shown schematically here, where the main part that you want to think about is this copper coil, right? And we can wind this using stuff that you can buy at Home Depot, right, into arbitrary shapes. So that's a nice feature of it. This is connected to an RF power supply, which puts in an RF electrical current. Don't ask me any details about that because I don't remember at the moment. I should have read up on that. This in turn generates a magnetic field that's oscillating in here. If we drop a metallic workpiece in here, like a crucible, like that tantalum crucible, that will couple to it and move electrons around and heat the workpiece resistively. What's advantageous about this is that it results in really localized heating and control of temperature gradients, depending on how we make the coil. In addition to that, it can result in stirring of the melt, which can be helpful in terms of making it more homogeneous. And sometimes, at least in my experience, if we do things like a solution growth in here, it can decrease the time it actually takes to produce nice crystals as well. It's sort of actively driving the reaction to go. This is useful for metals and non-metals. As long as our container is metallic, this is going to work. Operating temperatures are variable depending on the strength of your power supply. Ours is a 6 kilowatt, but there's much more powerful systems out there, and how many wines you make and the diameter of this and so on. But it's pretty straightforward to get to temperatures as high as 1700 degrees C. And that's significant because the resistive furnace that you're going to buy from MTI is probably going to get you to 11 or 1200. You can spend more money and buy a nicer furnace and get to 1500. But you've already run into a limitation, and that is that the quartz tubes that you're probably going to want to use start to soften around 1200. So the upper limit for our, well, and I should say you can buy an even fancier furnace at higher temperatures, but it's going to break all the time. So this is one way to get around a lot of these problems because you can access these sorts of temperatures and you can create sort of arbitrary environments to contain them. Right. And in addition to this, you just have a nice ability to control your gas environment. In our system, we have it hooked up to a gas purifier. We put really clean argon gas in during these growths. Okay, so now we can control the temperature, how quickly we cool and heat, temperature gradients, things like that. And we can even, oh, I have one more cool video. All right. So this is just the induction furnace in action. What this is a counterwound coil that some research experience for teachers people made. That's a piece of aluminum metal sitting in there. Of course, because we have a magnetic field, we can levitate this. That has advantages in some cases, because if you don't have a crucible, then you don't get impurities into your sample. That's another sort of technical thing to think about. The main point that I want to make here is just to show you how quickly we can heat this thing up and how focused the heating is. Right? It's really just on the sample. So we go from room temperature. Yeah, it's amazing and it's incredibly fun. And we are well above 1100 degrees C now with no effort whatsoever. Right? So this is really fun. I hope no one noticed the bare legs, with no safety equipment in the background. Okay. So that's the induction furnace in action. And let me tell you one more application of this. And that is, everything's about controlling how you're going to nucleate crystals. And that's shown here. Well, I don't have a very good video. But basically, we've got a crucible here. We've created a melt inside of it. And then we can dip a pull rod into it. And this, by the way, is an incredibly primitive pull rod. It's just a rod of alumina that we sharpened into a point. You can do a lot better than this. Anyways, you can dip this down into the melt and slowly withdraw it, and you can produce large single crystals like this that you probably would want for neutron scattering experiments. But the devil is always in the details, and these are not just trivial experiments, but they're doable. Okay, so I think that what I'm going to do now, because we already heard about flux growth, is to not say too much about it. I'll go through this quickly and just mention that when you're doing flux growth, there's sort of a standard approach that people take, and that is to think about the usual suspects. Right? Like, how do you choose a flux to grow your material in? Well, one way is to just look at these binary phase diagrams and sort of, do what we talked about earlier. The other is to use other fluxes, other materials with low melting temperatures that you might be able to dissolve elements into, and you might be able to grow the desired material out of. Keeping in mind that ternary and quaternary phase diagrams have all sorts of solidification boundaries and phases in them that we don't know where they are and what they are. The approach is generally to bring in the usual suspects, and that can include things like salts or elements like aluminum, gallium, indium, zinc, antimony, bismuth. And then, like I mentioned, these binary eutectic mixtures can be really powerful. So it's nice if you're going to make something out of 3 elements to go and look at their binary phase diagrams and look for a eutectic. Then maybe you can just use that and not have to bring in any of these other friends. And that might actually allow you to grow things without too much trouble. All right, so I'm not gonna tell all the details of the multi-metal flux growth because we heard about it, which is fantastic. But it's basically the same process. And by the end of it, as we already saw, you can produce really beautiful, and sometimes large single crystals. And there's two other things I want to say here. One is that sometimes people will tell you that their flux grown samples are ultra high purity. Maybe they are and maybe they aren't. Who knows, right? You have to do the work to figure that out. But one thing that is almost always true is that they form with facets, right? And this is a huge advantage because if you have a facet, it'll reflect the underlying crystalline symmetry. And sometimes you have a pretty good shot at guessing what the principal directions are. That can save you all sorts of time in your actual experimental approach. All right, so this brings me more or less to the end. When we're doing these new materials physics things, we're basically following a three-step process that we're going to do over and over and over again. We're going to make things, we're going to measure things, we're just going to repeat that over and over. What you've heard about so far is this step, and I'm going to put all of this off to another day. I'm going to quote Winston Churchill. I don't know if this is the right sort of place to do that, but I think this is very appropriate. He said, this is not the end, not even the beginning of the end, but it is perhaps the end of the beginning. And I think that once you've grown a crystal, maybe you can start to feel that way, but it continues to go on and on. And just to give my perspective on all this at the end, a little bit of a philosophical viewpoint, I think that the search for new quantum materials remains exciting and unsolved. Hopefully you've gotten some flavor of that out of this talk. I think that both serendipity and materials refinement are both key factors in leading to discoveries. To do this, physics, chemistry, and material science really have to work together in harmony. I really do think that this type of science is an ideal training ground for the next generation. You know, when you go into experimental labs with some fancy technique, the instruments are nowadays pretty often kind of black boxes. You understand what the measurement means, but you may not really have the chance to know what it's doing, right? Because who wants to take apart a very expensive thing? This is a problem. But with crystal growth, you really can get in on the ground floor and build things from scratch. So you can have complete mastery and control of your apparatus. And then finally, and I think this is really important, I think that crystal growth inspires awe, right? Like when you open a tube of new crystals, you see this incredibly beautiful collection of things. It may be a new material. It may be the first time that anyone will have measured the behavior that it shows. And in my opinion, this is really like rocket fuel for discovery because it makes you feel, you know, a certain way about nature that is just really motivating. So with that, I'd like to acknowledge the funding from the Mag Lab and from grants, and I'll just be glad to take any questions.
Okay, time to go. Yes.
So I have very nice. I have a question regarding the structure melting. So I think that some of the principles are relatively similar to cooking zone, optical cooling zone. They have local PD, you can have a temperature gradient, and yeah, and you can pull the samples. So how does it compare to the cooking zone method?
Yeah, it's a good question. So at the most basic level, it's the same, right? This is both of them are direct melt methods, and they're designed to control nucleation for a congruently melting compound. But in practice, they're different. I think the most obvious difference is probably that floating zone is usually applied to materials that are not very conductive. And it was designed, you know, specifically for that purpose. It's hard to grow oxides by any other method, at least these large single crystal ones. So, you know, with the optical float zone, you just have focused light and you're heating the sample. What else? I mean, in practice, yeah, there's another difference. And that is that in the float zone, you know, you tend to have a feed rod and a seed rod. That's definitely not part of what, at least how we've done it in the induction furnace. Although you could probably imagine doing it that way. You could probably build an apparatus that would do that. Probably Yeah, probably. There's differences in the way that convection works in the melt zone too, right? Because in the optical float zone, you're creating a melt zone, but any convection is going to be sort of due to your ambient conditions, right? You're in gravity. There's cold, hot, cold. You know, those sorts of things are going to change the way that convection works. And in fact, that convection really does impact the crystal growth. In an induction furnace, there's a magnetic field that's breaking the axial symmetry, and that changes the way that the melt does its convection. I don't know anything quantitative about those things, but I think that's what you would think about.
It might be slightly like technical or practical, but with the molten metal flux, recently I've been doing like magnesium tin or like say galvanium, cobalt tin. And sometimes when I was doing like the flux method, when I was like spinning it, I will still see there are some like tin defects where like surplus tin in my sample. Is there any way that we or I, you know, like researchers can reduce like surplus tin in this?
This is one of the main aggravations of multi-metal flux growth. So the first question that you have to ask yourself, and I think you probably did, is whether or not the tin is present as an inclusion or on the surface. If it's on the surface, the problem's not so bad because you might be able to etch it without destroying the sample. And hydrochloric acid, for people who don't know, is a good etchant for tin. If it's inside the crystal, much harder. And I think my advice, but it's probably nothing new to you, is that to try to get rid of inclusions, you have to try changing either the chemical composition profile to begin with, or the cooling profile.
Right.
And then it's really the hard work of trying it over and over again. Sometimes, by the way, that's possible. That's something you can do. Some labs do that all the time. Other times, if your elements are too expensive, you run into some pretty significant problems right away. One other thing that you might try. Let's say that you grew a batch of crystals and they had tin inclusions and you weren't very happy and it had expensive elements. You might take some of the crystals that you grew, grind them up, maybe not too fine, but just grind them up, and then use them to seed your next growth. And I have had the experience that will result in, different formation properties. So seeding your growth with the material you want does or can impact the way the growth actually proceeds. One other thing, let me make one more comment about all this. Our growths very often are a black box, right? You put it in there, you let the growth happen, and then you see what happens. There are facilities now, though, for neutron scattering, where you can actually watch the growth as it happens. You can do diffraction and see what phases form. I don't know that this would actually help you, but I think it's a powerful new way to get insights about what's actually happening.
Just one comment as well, and this reminds me of a former speaker in our school, Brian Sales, who has a great story about, I forget the comment.
Is it the one with the drawers? Opening and shutting drawers. I don't know. Tell yours.
Crystal, they grew the first try, they grew centimeter sized crystals in Flux Road. And then they could never reproduce it. Finally, they went back and realized that in their notes they had at the high point had taken the crystal out and just stirred it and put it back, and that actually reproduced the large crystals. Yeah. So you're at this high temperature, and it's very small perturbations can really affect the growth. Yeah. Stirring, temperature gradient, where it's in the furnace, all these things. Unfortunately, it takes just trial and error to try to see what works.
There's a closely there's a closely related story to this one where someone had their furnace on top of a drawer set that had all their tools and stuff in it. And they would do growths in that furnace and they'd get the big crystals. And then they'd do growths in another furnace and they got little tiny crystals. They couldn't figure out why. Eventually they figured out that it was because people were coming in and opening and shutting the drawers all day. So mixing matters a lot. And now we're really getting into the weeds. But I've read in this book by Pamplin that back in the 70s, another thing they would do is take something like boron oxide and put it into their melts, and it would sort of cap the melt. And this was with salt fluxes at the time. And that had a big impact on the types of crystals that they would get, because the junk would sort of, get sucked up there, and it would just leave a really clean melt. So there's so many things you can try, but you have to perturb the melt. That's sort of the bottom line.
My question was actually like about what you have been recommending. So is there a way to control like growth nucleation? Like could you grow something like epitaxially by putting something which doesn't melt inside the flux tube?
Great idea. I don't have any experience with that, but I think that if you could have something that you put into the melt that wouldn't dissolve into the melt, it seems like that would impact what grows and how it would grow. It might grow nicely. I mean, actually I do. In a way, I do have experience with that. So the crucible itself is a substrate for what's growing in there. And so a few years ago, I was working on some flux growths. We were actually working on some transuranic things. So we needed to do work on, larger, more standard things, and then scale them down, because we wanted ultimately to be using just a little tiny bit of material. And what we found out, this actually was happening even for the uranium things we were growing, because that was our chief element. When we grew it in the big crucible, we'd get one phase, and it was something called a 1-2-20 phase, sort of a large unit cell material. And then when we changed it and went down to our little tiny crucibles and had the same ratios, but just less melt, or in other words, there was more surface area to melt ratio, we got a completely different phase. And it was another cage-like phase, but it was like its own thing. So yeah, I think that's an interesting thing to think about. Beyond that, I don't know.
And also something called liquid phase epitaxy, which is exactly what you're saying. Have a substrate that you bring in contact with the melt, it grows, you grow garden. Any final question? Yeah, I guess you did a good job.
Don't be shy later.
So we will take a 2-minute coffee break. There's going to be coffee still downstairs, and we'll be back at 11. Remember, it's nice.